HLAA, complex numbers, day number 7. Topic for today is one that we have visited first semester, which is proof by mathematical induction. Just a reminder, since it's been a couple of months since we've talked about this, 3 basic steps, well, 1 basic step, but 3 steps in all. First, we're going to come up with a statement, which is what we're trying to prove. And with that statement, our first step is to do the basic step, which is to set a foundation of truth. So we want to show that P sub n, or P of n, is true for the first available n. Many times that's n equals 1, it might be n equals 2, depending on the statement itself. Our second step is called the Assumptive Step. And in this step, we are going to assume that our statement is true for some k. Right, that sets a general foundation. And now in the third step, called the inductive step, we are going to then prove that the k plus 1th term of this statement would also be true. Okay, and in that, if the kth term is true, so if P of k is true, k is generally defined here, right? It's not a specific number, and P of k plus 1 is true, then by that same property, then P of k plus 2 must be true, and so on. Because to P of k plus 1, P of k plus 2 is the next term. So by finding and proving the inductive step, we are showing truth for the next term. And if the next term is always true, then the statement would be true for all terms in the positive integers. Okay, so let's go ahead and get into an example. All right, so for this lesson, I'm just going to do one example. And that example is going to be proving de Moivre's theorem using math induction. So what I'm going to do is I'm going to prove that z to the nth power is equal to r to the nth power times cis n theta. Now I do have to define a couple of things. To start with, I'm saying that n is in the positive integers, and z is equal to the modulus of that complex number times cosine theta plus I sine theta. So I've got a foundational definition to go off of. All right, so first thing we do is we're going to let P sub n, keep saying P sub n, P of n be the statement highlighted above. So I'm just going to highlight it. All right, and it's going to be this statement right here. Okay, so I'm going to prove that, and P of n is basically a shortcut way of saying that statement. Okay? All right, so let's get into it. The basic step. Okay, step 1, basic step. So what I want to do is I want to show that P of n is true for our first available n. Well, our first available n will be n equals 1. That's the first positive integer in that set. So I want to show truth for P of 1. Okay, so z of 1, based on this, should equal r to the first cis 1 theta. Okay, so z to the first power. Well, if I take z over here, that would be r cosine theta plus I sine theta, which of course, by definition, would be r cis theta, which is true. Therefore, P of 1 is true. Okay, typically you'll get 1 mark for showing the basic step. Okay, the assumptive step. Okay, basic, very simple step. I'm going to assume P of k is true. Okay, so what does that look like? That just means that z to the k power is equal to r to the k cis k theta. So I'm substituting in a k everywhere I see an n in my original statement, and I can now assume that that's true. I'm going to assume, since I've made a foundational find here, so to speak, with n equals 1, I can generalize it in terms of n equals k. Okay, now comes the work. Right? We're going to get into the inductive step. So here we go. In the inductive step, our objective is going to be to prove that the next term will always be true. Is true. That the next term for this statement will always be true. Some poor handwriting there. Let me erase that. There we go. Let's try that again. Much better. Okay. All right, so let's write this out. Based on the inductive step, we are trying to prove the following. So I'm going to start on my left side here, and I'm going to show equivalence to the right side. And again, in math induction, or any proof for that matter, you can only work one side at a time. Otherwise, your proof is invalid. So based on properties of exponents, I could say that z to the k plus 1 is the same as z to the k times z. Okay, and z to the k is equal to, based on the assumptive step, so I'm going to plug the assumptive step in here, r to the k cis k theta. And z, or z to the first, is r cis theta. Now, I've got some work to do here. I've got to use some trig. So what I'm going to do is I'm going to take the r to the k and the r to the first and bring them together. And then I'm going to expand the cis k theta and the cis theta. So cis k theta will be cosine k theta plus I sine k theta. And cis theta is cosine theta plus I sine theta. Okay, now I've locked this in. What I'm trying to prove is I've got r to the k plus 1. Well, by definition, using properties of exponents, that will be r to the k plus 1. So I've kind of got that locked in place. Now what's interesting is I am going to get an expression when I FOIL these two binomials out. Okay, let's see what that will equal. I will have first times last, or first times first, cosine k theta, cosine theta. Outside will be I cosine k theta, sine theta. Inside will be I cosine theta, sine k theta. And last will be I squared, which is a negative 1, sine k theta, sine theta. Okay, let's analyze this. I've got a real component here and here. Cosine k theta, cosine theta, minus sine k theta, sine theta. By definition, let me bring everything else down here. This is a compound identity for trig and will be equal to cosine of k theta plus theta. Okay, now our imaginary component, cosine k theta sine theta, cosine theta sine k theta. That by definition of course with an I attached will be sine of k theta plus theta. Okay, the trig's never going away. If you want it to, that's sad because it's not. Okay, so by definition of complex numbers in modulus argument form, cosine k theta plus theta, well, let's look at k theta plus theta. That's actually equivalent to k plus 1 theta. And look at that. That's exactly what I was looking for, right, in our inductive step. Thus, I will have cosine k plus 1 theta plus I sine k plus 1 theta. And going one step further, putting this in cis form, I have now proven de Moivre's theorem using math induction. So if I were to, again, allocate some marks here, just off the top of my head, I would likely, like I said, for step 1, that basic step, I give you a mark there. I would say probably a mark for identifying, this property of exponents splitting z to the k plus 1 into z to the k times z. And then I would probably go mark here for the expansion, and probably mark here, and maybe one more right here. Typically you won't see that you'll get a mark for the last step there because a student might just say, hey, I'm trying to prove this, and skip everything in between and rewrite it, right? So you're not going to typically get that mark there. So you can see though that you got 5 marks there. Let's go with one more mark for our statement. So we would say, therefore, since p of 1 and p of k plus 1 are true, then p of n is true for all n in z plus by mathematical induction. Okay, like I said, allocate a mark there, and you got a 6-mark question. All right, so now what have we done? We have opened up de Moivre's theorem. It is now applicable and available to us in every way, shape, and form on the set of positive integers. All right, guys. Now, this actually does apply outside the positive integers. It applies to all real numbers, but in this proof, I just worked specifically with the positive integers. All right, de Moivre's theorem. Boom, gotcha. See you in the next video.